Hi everyone, now we are going to discuss on a three-phase half controlled, which is also known as a semi-converter with RLE load. So we are having 3 thyristors and 3 diodes, and we are using a symmetrical configuration, that is all the thyristors are in the upper half and all the diodes are in the lower half. And we have our thyristor T1, T3 and T5 occupying the positive group, and D2, D4 and D6 occupying the lower group. And there is an inherent freewheeling action which is made possible by having a diode along with the thyristor. So if we are having the freewheeling action which is made possible using the thyristor and the diode, then it will result in higher losses because of the two conducting devices, which can be avoided by connecting a single freewheeling diode across the system. Now, there are different instances of which we need to draw the waveform. The first one is with the firing angle alpha equal to 0 degree. So we have already discussed in the earlier session that alpha equal to 0 degree corresponds to omega t equal to 30 degree, since we have taken the phase voltage waveform as the reference, that is omega t equal to 0, we have taken the phase voltage. So therefore, if we are taking our firing angle alpha to be 0, then it will be same as the waveform which we have obtained for the full converter, because it is ideally it is going to act as all the devices will be acting as an uncontrolled device, because your firing angle alpha is 0. So therefore your output voltage will only be the pulses through here, again this one, again like this, again it goes. So it will be same as what we have obtained in the previous lecture, and therefore we will not be plotting that particular value for firing angle alpha equal to 0 degrees. Now we are going to plot the output voltage waveform for firing angle alpha equal to 30 degrees. So in the same way what we have discussed in the earlier convention, this is the point when alpha equal to 0, corresponding to this particular point, which is omega t equal to 30 degrees. Now our alpha is 30 degrees, so 30 plus 30, 60 degree you have to trigger on the thyristor T1. So I will mark here it as T1. So T1 will be conducting for 120 degrees, 1, 2, 3 and 4. And the diode D2 is an uncontrolled device, and it start conducting at this instant. So therefore here I can draw it as D2 is going to conduct. So now you can see that T1 and D2 are conducting. So for alpha equal to 30 degree, the thyristor T1 and the diode D2 comes into operation, and we can see that the waveform is going from through T1, RLE, then D2 and to the point Z. So therefore the voltage which comes across the system is nothing but VAC. So that is nothing but this one. This is nothing but your waveform corresponding to VAC. So it is VAC. After 120 degrees of conduction, the diode D2 becomes reverse biased, which is seen from here, that the diode D4 comes into picture. So that means at this instant diode D4 starts conducting and here T2 starts conducting. So each of the devices will be conducting for 120 degrees, and after T1 conducting for 120 degrees, T3 is being fired again at an alpha 30 degrees. So this is the instant at which we are triggering on the thyristor T3. Now the devices which are conducting at this instant is nothing but T3 and D2. So T3 and D2 indicates it is B T3 RLE D2 and to the point C. So therefore VBC is appearing across the load as V naught. So therefore during this instant from this particular point till here, the voltage across the device is VBC. So this is VBC. Since the diodes are uncontrolled devices, here the D2 will get reverse biased and D4 will start conducting. So therefore we can say that now T3 and D4 are in the conduction mode, and therefore here you can observe it is T3 load and D4 back to A. So therefore the voltage which is coming across the device is nothing but VBA. So that VBA we can plot it over here, which is corresponding to VBA like this. It will reach over here, but you can see that the diode again it will be conducting for another 120 degrees, and T3 will also be conducting for another 120 degrees. So till here it is VBA. Now again after T3 the device which comes into operation is T5. So T5, you can see it from here. This is the point for alpha equal to 0 for thyristor 5, and this is for alpha equal to 30 degrees. So correspondingly you can see it over here. This is the point at which I am triggering on the thyristor T5. So now there are two devices which are conducting, that is T5 and D4. We will observe it here, T5 and D4. So it is from the point C, T5 RLE, then D4 to A. So VCA is nothing but the voltage which is coming across the load as V naught. So that we will be plotting it over here for the waveform VCA. So the corresponding waveform is, this is VCA, so which is mentioned over here till here. So again at this instant of time you can observe it here, the next thyristor D6 comes into operation. So here I will mark it as D6. It will continue for 120 degrees, and this will be continuing for 120 degrees. So when T5 and D6 are conducting, you can see that it is point C, T5, RLE, D6. So VCB is the voltage which is coming across the load as V naught. Therefore I can plot it here like this. So effectively we can say that only the alternate pulses are changed. See, this pulse is not changed, but here because of the firing of the thyristor you have a change in this pulse. Again the second pulse there is no change. Again for third pulse, a change is there. So alternate pulses are being changed while we have our semi-converter operation at alpha equal to 30 degrees. Now we can complete the entire figure for the complete operation. So this is how the complete waveform of the output voltage looks like for alpha equal to 30 degrees. Now we can also draw the current waveform I0. Here the current will start increases and then it gradually comes down. Again it will increase like this. So this is how the current waveform will be looking like in the case of alpha equal to 30 degrees. We are going to discuss for the firing angle alpha equal to 60 degree. Alpha equal to 60 means omega t equal to 30 plus 60 degree we need to fire the thyristor. So that is, this is 30 plus 60, 90 degrees. So here my thyristor T1 is fired. So here I am going to fire my thyristor. So this I will mark it over here, it has T1. Now along with the thyristor T1, one more device from the lower half has to conduct. So here you can see that after T1, the device which is getting forward biased is D2. So therefore T1 and D2 will start conducting at the same time. So now we will see which voltage is going to appear across the load. So it is T1 and D2. So it is from A, RLE, D2 and to the point C, and therefore we can say that it is VAC is going to appear across the load. So VAC is going to appear across the load and it will still continuing for 120 degrees. So VAC will be coming into picture. So both the devices will be conducting for 120 degrees, 30, 60, 90, 120. Now at this instant you are again going to fire your thyristor T3. So that is, here it is alpha equal to 0, 60 degree means one step, second step. So with the corresponding that we can say that the T3 is being fired. So along with T3, the device which is going to conduct is nothing but D4. So that will again continue for 120 degrees. Now the voltage which comes into picture over there when T3 and D4 are conducting, we will see it from here. It is T3. So from the point B, T3 RLE, then D4 to the point A. So VBA is going to appear across the load voltage. So therefore the corresponding waveform is this one. Now again at here T3 has stopped conducting and the thyristor which is fired is T5 at 60 degrees. So at this instant I am going to fire T5. So the devices which is going to conduct at the same time is T5 and the diode D6. So therefore it is T5 and D6. So when T5 and D6 are conducting, we will see it from here. It is point C, T5, RLE, then D6, then to the point B. So the voltage is VCB is the voltage which is going to appear across the load. So that VCB we are going to plot it now. So this is the corresponding waveform of VCB. So I will plot it like this. Now we can continue it over here. VCB. So here also it is T5 and D6. So this is how your output voltage, which is going to appear across the load for alpha equal to 60 degrees. It for the firing angle alpha equal to 90 degrees. So this is omega t equal to 30. So from there 90 degrees, so 90 plus 30, so 120 degrees you need to fire the thyristor. So 1, 2, 3, 4. So here I need to fire the thyristor. So the thyristor T1 is fired at this instant, and along with that the diode D2, which is already in the forward biased condition, will start conducting. So that we can refer it over here of the same sequence, and therefore I will draw it over here. This is for T1 and the diode D2. So when T1 and D2 are conducting, we will see it from this figure. T1 load D2 to the point C. So it is VAC is going to come into picture. So therefore the corresponding waveform is nothing but this one. So I will plot it from here. VAC. So this is about the VAC. So we already knew that the diode D2 gets reverse bias at this instant. That is visible from this particular figure. Or we can say that after this instant it is going to the negative. So this VAC is going to become more negative. VAC becomes more negative means the point C will be becoming more positive when compared to the point A, and therefore the diode D2 gets reverse biased. And basically the thyristor T1 will be still continuing in the on state. Why? Because the current has not come below the holding current, and therefore it will still in the conduction mode. So effectively we can say that T1 and D4 becomes conducting, but we have kept a freewheeling diode in order to take that freewheeling path. So this freewheeling diode gets forward biased because of this negative supply from the point A, and therefore the current will be flowing through RLE and the freewheeling diode. And therefore that means your output voltage terminals are short circuited, or effectively your output voltage V0 is 0. So during this instant it is the freewheeling diode which is going to conduct. So therefore your current will again start reducing while the freewheeling diode is conducting. Now at this instant you can see that the thyristor T3 is triggered at an angle alpha equal to 90 degrees. So effectively this was alpha equal to 0. So 30, 60 and 90. So when we are tracing it down, so this is the point where I can turn on the thyristor T3. So during that time the D4, which is already forward biased, will also start conducting. So we will see which voltage comes into picture over there. So it is BT3 load and the D4 back to A. So it is VBA which is coming across the load. So we will plot it over here. VBA and after that when VBA starts to reverse, the D4 gets reverse biased, and T3 it will still continuing because the current has not come below the holding current, and therefore the T3 and D6 is yet to conduct, but the freewheeling diode gets forward biased because of the negative supply over here. So therefore again the current will freewheel through the freewheeling diode R, L and E. So therefore the output voltage will be 0, current gradually reduces, and this is for the freewheeling diode. Again you are going to fire your thyristor T5 at alpha equal to 90 degrees, which corresponds to this particular point, because we can just refer that this was for 60 degrees, so 90 degrees will be plus 30. So at this instant I am going to fire the thyristor. So which thyristor? It is T5 and the diode D6. So when T5 and D6 are conducting, it is from the point C, load, to the point B through D6. So it is VCB which is coming across the load. So this is VCB. So now we can also complete the rest of the figures for the complete waveform. This is how the complete waveform of voltage, firing sequence and the current for alpha equal to 90 degrees. So FD is indicating your freewheeling diode FD. So during that time the output voltage is 0. Now we are going to plot for alpha equal to 120 degrees. So when alpha equal to 120 degrees means alpha omega t equal to 150 degrees. So it is, this is 30 degrees, 60, 90, 120 and 150. So this is the point where I am going to fire the thyristor T1. So when thyristor T1 is fired over there is a diode which is already in the forward biased condition, that is nothing but D2. So D2 also comes into picture. So when T1 and D2 are conducting, you can see it over here, it is point A, T1, RLE, D2 to the point C. So VAC is the voltage which is going to appear across the load. So therefore the corresponding waveform, so this is nothing but VAC. So we will be plotting it like this. And what happens over here, which you already discussed, that the freewheeling diode comes into picture. So this is FD. So that time the voltage is 0. Now the freewheeling diode is giving a path for the stored energy in the inductor to return through the freewheeling diode and dissipated at the resistance. So once the entire energy is being released, then the only voltage which comes across the load is nothing but the EMF E. So therefore during that instant of time, this will increase to your EMF E. So that time no thyristors are conducting or no diodes are conducting. And after that only your T3 is being fired at a delay of 120 degrees, and therefore the voltage which comes into picture over there is nothing but VBA. VBA. So the devices which are conducting are T3 and D4. Once it reaches over here, like our previous explanation, the freewheeling diode comes into picture and therefore the load voltage comes to 0. So after that the inductor will release all the energy which is being stored, and therefore only the EMF E comes into picture. So during that period none of the thyristors or devices will be conducting. Then again the next set of thyristor is being fired at alpha equal to 120 degrees. That means it is T5. So you can refer it over here. So this was for 90 degrees and this is for 120 degrees. So now the new firing will be happening over here. So that time the thyristors is T5 and D6. So when T5 and D6 are conducting, it is VC T5 load, then D6 to the point B. So it is VCB is going to come. So this voltage is nothing but VCB. And after that the freewheeling diode comes into picture, referring to our earlier explanation. So the load voltage is 0. Again the entire energy stored by the inductor is released. So the output voltage becomes E. So this is when the thyristors are conducting. So basically when you are referring to this figure, there is a point where no devices are conducting. When no devices are conducting means the current is 0. So if you are assuming a discontinuous conduction mode, so the current will increase, comes to 0, again it will increase, comes to 0, again it will increase, comes to 0. So because no devices are conducting for certain period of time. Now we can complete the entire figure. So this is the complete figure for alpha equal to 120 degrees. The load voltage waveform, the firing of the thyristors and the diodes, and the load current. Thank you.